Hey guys, Mr. Betts here. Besides long division, which we've looked at in another video, we can also complete the square to manipulate an expression in an integral or an antiderivative problem to rewrite it in a way where we can actually take the antiderivative. So let's start by looking at a couple of derivative rules where this might be helpful. So remember with antiderivatives, if we have an expression like this that we want to take the antiderivative of, we're asking ourselves, what did we take the derivative of to get that? Well, notice that both of these have polynomial, specifically quadratic expressions in the denominator, and completing the square is a tool that we can use to manipulate quadratic expressions. So when we're going to be using this is going to be rewriting integrals so that we can write them in a form where the antiderivative will either be inverse of tangent, so arctangent, or arcsine. So let's kind of look at this a little bit more generally. With the arctangent derivative, if we have something that we can rewrite in terms of u, so some other expression squared in the denominator, so 1 plus u squared, then usually we're going to be able to take the antiderivative and get an arctangent expression. Likewise, if we can rewrite it as the square root of 1 minus some expression squared, then that means that we're going to probably be able to use arcsine. Now, this something up here is going to have to be a constant in both cases. So we're going to have to do a lot of algebraic manipulation to do it. And part of that process is going to be completing the square. So let's look at a specific example. And the problem with examples like this is that it's not obvious looking at an expression like this, knowing that we're going to end up using arctangent. However, using completing the square, we can rewrite the denominator as something that looks like this with the 9 down there. So notice that I factored out this, and the trick is figuring out what we can do with completing the square and algebraic manipulation to get from one expression to the other. Once we've done that, then we can use substitution with this expression and say u equals x plus 4 over 3, and we can use that to get an antiderivative that's arctangent. So let's just do a quick refresher on completing the square first. So the idea here is we're going to ignore the constant. So I'm going to rewrite this expression, x squared minus 8x, and then I'm going to put the plus 20 here off to the side. So I'm going to focus on the x squared x squared minus 8x, and I want to write an expression here that can be factored into a square. And the process here is we're going to take the linear term, the coefficient of the linear term, that negative 8, we're going to divide it by 2, and then we're going to square it. So negative 8 divided by 2 is negative 4, and then we square that and we get 16. So what we're going to do is we're going to add on 16. Now, by adding 16, I just increased the entire expression by 16, and I don't want to change the value of the expression because I want to use equal signs between my steps. So I'm going to subtract 16. So the next thing I do is I actually factor that expression that I have underlined there. When we factor that, you're going to get a perfect square. So 16 is 4 times 4, and so we're going to do x minus 4, x minus 4. That's x minus 4 squared. Notice that it's just that, so x minus 4 squared. And then 20 minus 16 is going to be plus 4. So this expression right here is equivalent to that expression, but it has a square in there, which is going to be useful to us. Okay, so let's look at how we can apply that completing the square to help us with evaluating an antiderivative. So what I want to do is I want to rewrite this expression in a way that it looks like this, 1 over 1 plus something squared. And if I can get it in that form, then I can use the arctangent as my antiderivative. So I'm going to go ahead and complete the square in the denominator. So I'm going to have 1 over, sorry, I need my antiderivative here and my dx here. So we're going to have x squared plus 8x plus 25. And then for the completing the square part, half of 8x, half of 8 is 4. 4 squared is 16. So I'm going to add 16 and I'm going to subtract 16. So I'm going to factor. I'm also going to change my order here a little bit. I'm going to put this out front just to put it in this form. It really doesn't matter if it's 1 plus u squared or u squared plus 1 in the denominator, but I'm used to seeing into this form, so that's what I'm going to use. So we're going to have the antiderivative of 1 over 9, so 25 minus 16 is 9, plus x plus 4 quantity squared dx. Now, an important part of this expression here is that 1 there. So I want to make sure that I have a 1. And in order to do that, I'm going to multiply the top and the bottom by 1/9. So I'm going to multiply by 1/9 here. I'm going to multiply the entire denominator by 1/9. So I'm going to do that for each term. And so we end up with the 1/9 on top. I'm actually going to take out front as a constant multiple. So we still have the 1 on top because I want that there also. Then we have 1 plus. Now this is going to be x plus 4 quantity squared over 9. And 9 is 3 squared. So that's going to be the same thing as x plus 4 over 3 squared. So x plus 4 over 3, and then that quantity squared dx. Now, having completed the square and manipulating it in a way that we have 1 over 1 plus some expression squared, now I can use substitution to evaluate this using arctangent. So I'm going to say u equals x plus 4 over 3 Now we're going to take the derivative. Du equals 1/3 dx. So if we divide term by term, it's going to be x over 3 plus 4/3. And that's going to give us dx is equal to 3 du. So making our substitution then, this is going to equal 1/9 integral 1 over 1 plus u squared. And then dx is going to become 3 du. Now, for the purpose of moving along a little quicker, I'm going to just make this a 1/3, because if you take 1/9 times 3, you get 1/3. Now this is just going to be 1/3. Antiderivative of that is arctangent of u plus c. So again, we took the antiderivative. At this point, we lose the integral symbol and we get our plus c. And then the last step is to substitute back in for u. We get 1/3 arctangent of x plus 4 over 3 plus c. So the completing the square was just one part of this problem, but it allowed us to write our integrand in a form that we could then use substitution to get an antiderivative with arctangent. Just another refresher with completing the square, we only want to do this with a coefficient of 1 on our x squared term. So the first thing we want to do on something like this expression is factor out that 2. And we can just keep the plus 20. We don't have to factor the 2 out with that. And so when we complete the square here, we're going to add 4. But when we're adding 4, we're really adding 8. So we're going to subtract 8 here. And so this expression then becomes 2 times x minus 2 quantity squared plus 12. So if we're completing the square and there's a coefficient here besides 1, you want to factor that out before you complete the square to make things easier for you. So if we have an expression like this, I'm going to go through this one a little more quickly than the last one. However, I do want you to see it. So I'm going to have 1 over 2x squared plus 4x plus 20. And then the completing the square step, we're going to add 4. So that's adding 8. So I'm going to subtract 8 to keep it balanced. So that gives us we're going to have 12 plus 2 quantity x plus 2 squared dx. So now we want to write it in that form 1 over 1 plus u squared. So I'm going to multiply by 1/12. So we're going to have 1/12. And then integral of 1 over 1 plus x plus 2 over the square root of 6 quantity squared dx. And if you're not sure where that square root of 6 came from, I divided this by 12, and then I took the square root so that I could put it in the square. And now we can do substitution. So letting u equal x plus 2 over the square root of 6 du is then going to be 1 over square root of 6 dx, and dx is going to be square root of 6 times du. So we can use that to make a substitution. And I'm going to put the square root of 6 out front. So we get square root of 6 over 12 times the arctangent of u plus c. And finally, we substitute back in and get that. So again, we're using completing the square as part of the process of rewriting an integrand in a form that we can use substitution to take an antiderivative.